Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 13, 2025, just yesterday. This paper introduces latent refinement decoding, a two-stage decoding method that boosts accuracy and delivers speedups of up to 10.6 times, with gains of 6.3 on human eval, 2.6 on MBPP, 2.9 on GSM-8K, and 3.8 on Math 500. The paper is titled Latent Refinement Decoding, Enhancing Diffusion-Based Language Models by Refining Belief States. And as we'll see later, the results are really impressive. In short, the method preserves soft belief states, then finalizes confident tokens, using KL divergence to decide when to stop. Alright, the introduction set the problem of losing information when undecided tokens collapse to a single mask. Figure 1 contrasts that baseline with the latent refinement approach. The top panel depicts low-entropy denoising that repeatedly remasks uncertain positions, which forces premature commitments. The bottom section illustrates mixed embeddings, meaning each masked spot carries a soft blend of likely tokens and the mask, so context can coordinate decisions before Phase 2 finalizes confident tokens. So, Figure 1 showed the mechanism. Table 1 reports how it pays off across code and math benchmarks. The table shows consistent accuracy gains, with the largest single jump around 6 points on human eval. Models also run faster because speed values greater than baseline indicate fewer decoding steps. Longer sequences benefit the most, reaching roughly 11 times speed on the biggest context. Improvements hold for both base and instruct variants, which suggests the method is robust across training styles. So the table just quantified gains. Figure 2 shows KL divergence dropping as steps proceed, which means the model's predicted distributions become closer to the final outputs. KL divergence is a distance between two probability distributions, so lower values signal agreement. The red line marks decoding starting after 20 latent steps, and the curves keep sliding towards zero. Figure 3 plots convergence ratios, and most cases stabilize by step 3, which explains why decoding finishes quickly. Well, the convergence plots set up the question of how often to refine. Table 2 reports an ablation on decoding schedules. Latent refinement means keeping uncertain tokens as soft mixtures before committing. The two-stage design leads the pack, with about 4.8 points on human eval. Variants that add repeated refinement rounds trail slightly and run slower, because once beliefs stabilize, extra passes add computation without guidance. So, Table 3 examines which components drive accuracy. Mixed embeddings, which blend the mask embedding with a weighted average of likely tokens, matter most because removing them causes drops of about 3 points. Latent refinement still helps, with smaller declines around 1 point. Early stopping barely changes accuracy, since it halts when KL divergence stabilizes. The two-stage design remains the strongest across tasks and sequence lengths. So Table 4 compares decoding variance and shows what drives speed. The table reports speed and an effective token count, which means how many tokens the system effectively processes during decoding. Removing latent refinement slightly speeds things up, but risks stability, while removing mixed embeddings slows convergence. Early stopping delivers the biggest acceleration because it halts once KL divergence stabilizes, with long sequences reaching roughly 10 times speed. The combined two-stage method keeps token counts lower, so it finishes faster without accuracy trade-offs. Wrapping up, two takeaways stand out. Preserving soft belief states with mixed embeddings avoids premature commitments, and the two-stage schedule with KL divergence early stopping boosts accuracy while cutting latency by up to about 11 times. The broader implication is a practical, drop-in decoder for diffusion language models, primed for further systems gains. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.